In this lecture, we give a very important example of a Galois category. So the example we want to give is that this covering space of X, this category with the fundamental functor, is a Galois category. So what is this category? So this category is the category of coverings of some space X, and the objects are just the covers. So they are given like this morphisms which sit over X, so going from Y to X. So these are the objects. So we have talked about objects like this in a category in our lectures on category theory. So by definition of a covering space, you can pick up a point, this X in space X, and then you can consider the fiber F inverse of X in this Y. So you pick up a small point X in the space X and you can consider the fiber right here. So this fiber is a discrete set. So this is just the definition of a covering space, and there are a large number of examples on this channel on covering space. So you can just search the channel for examples on covering space. So then we can consider the following functor. It goes from this category of coverings of a space X to sets, which just basically sends a cover, so a cover like this, to a fiber, this a discrete set. So this fiber, which is a discrete set, will lie in sets, and so any map like this, so Y is a cover of X, so corresponding to this point X, you land up in sets, which is F inverse of X. So you feed in F and you get F inverse of X. So what we are trying to say is that this particular thing with this fundamental functor is a Galois category. So before we proceed any further, the first thing we will have to do is form proper maps between two covering spaces. So say we are given this. This is one covering, and then you have another covering, say Z. We want a map from Y to Z. So say this map is phi. And obviously this has to be defined in terms of the covering space, and the analogy we have is of that of covering spaces in topology. So it is important that you know the definition of a covering space in topology before we proceed here. So to do this, we have to prove a lemma. So for Galois category, to show this is a Galois category, we have to see all these axioms G1 to G6 of a Galois category are satisfied. But before we do that, we have to make sense of this map phi. So this lemma is going to make the sense of this map phi. So say X, Y, Z be topological spaces, and then you have this map F, which is a covering, and then you have a map G from Z to X, which is another covering. So these are finite coverings. So then if you take F inverse of X, it will have finite number of elements in it. And say H Y to Z is a continuous map with F is equal to G times H. So this map is H. So what we want to do is we want to construct this map phi, which will take a discrete set associated with covering Y to discrete set associated with covering Z. So then for any X in this space X, there exists an open neighborhood U of X such that F, G, H are trivial over U. So that is what is the definition of a covering space. So we need, for F and G, this will just follow from the definition of the covering space. So what we need to do is we have to do something for H. So that is precisely what this phi is going to be. So they are trivial over H. So that is, there are finite discrete sets D and E. So everything here will be clear once we start drawing diagrams. So there are finite discrete sets D and E and homeomorphisms alpha from F inverse of U to U times T, and beta G inverse of U to U times E, and a map phi from D to E such that the following diagram commutes. So this diagram looks quite a bit, but this will be clear as we start proving this lemma. So this lemma is just a lemma in diagram chasing, as we will see immediately. So this phi is not very difficult to construct. So you can pause here and look at this diagram, and let us start now proving this lemma. So let's start with the proof. So we are already given two coverings, F and G. So you can find two neighborhoods v1 and v2 of this x which lies in our topological space x, and we have the following homeomorphism. So this is just from the definition of the covering F. This is just from the definition of covering G. So this covering F comes from this space y going to x. This covering G is coming from z going to x. So you have this F, and this is a homeomorphism. Alpha is a homeomorphism from here to between these two sets. So they are homeomorphic. So you can take an inverse and go back. Similarly, these two sets are homeomorphic. You can take an inverse and go back. So these two are just definitions which come from the these covering spaces F and G. So this is what it means to have a cover. So this D and E are finite sets. They are finite coverings. So now you set V equals to V1 intersection V2. Then instead of V1, you are just going to put V here. And then instead of V2, you put a V here. And this is the set, this is the mapping H you get. So that is what we have, this mapping H. So what we want to do is we want to construct this mapping phi from D to E. So because from it just carries U to U via an ID map. So what we want to get is a mapping phi. So now you already know that alpha is a homeomorphism, so you can take its inverse. So you travel in this direction first, alpha inverse, then you travel in this direction, then you travel in this direction, and this traveling should be same as this traveling. So that will what is going to give you map phi. So this pair, say V comma D, goes here, here, and comes back here, and it can go here precisely because this is a homeomorphism by definition of a covering space. That is what is going to give you phi. So this B beta H alpha inverse. So first you apply an alpha inverse, go back, then you apply H, then you apply beta. So you can go from V times G to V times E. So you're given by some map. This VD is getting mapped to V comma E. That is the mapping. So for any fixed V in this space V. So we have constructed this map phi, but we have to do it for every open set U. So this phi was easy to construct. It just pops out from the definition. But what we need to check is that this is true for open sets. So there exists an open neighborhood U of X. So ideally we just want to set U here, but we want to make sense that this U which is open here, this map should make sense right here. So now that's what we are going to do. We are trying to make sense of this map. Instead of V, we want to put in U. So you set E as phi V of T. So phi is just going to be this map, but this phi is related to this V here. So this E you're saying is phi V of T. So this is what you set it. Now instead of V, you could talk about any element X in this set V, because ultimately we are going to replace this V by some set U which is neighborhood of X. So we need, instead of this particular V, we need this phi of X. So this phi is dependent upon this map phi of X, which is fine because we are defining fiber as relating to a particular point. So now we have two maps going into E times E. So first you have the simple projection map from V times D, you go to D, then you have this map D, you apply phi to it, you get phi of D. So this is where phi of D, the first component, comes from. The second is you have this V times D to V times E, you apply our standard map, then you project it to E. So here we said that this map V comma D gets mapped to V comma E, where E is phi V of D. So this is getting mapped to V phi V of D, and then you are taking care of the second component and putting it right here. So you have a projection map right here. So the diagonal is precisely when these two are equal, and this is this diagonal is open in E times E. And the idea is now that you have to show that there is an open neighborhood of X times D. So again, the diagonal is just this equality, and this diagonal will be open in E times E. So the idea is you take anything here, say some point X in D, this is obviously going to get mapped into the diagonal, because you will have an equality right here like this, because this will be phi x of t, and both of these have to match if you are going from here or you're going from here. So both of these are continuous map, because that's the way we have constructed this. Phi is just taking homeomorphism h and beta, and h is given to you as a continuous map, alpha as a homeomorphism, beta as a homeomorphism, so this holds. So you have this continuous map into E times E. That is pretty much it. So this will get mapped into the diagonal, and the diagonal is open. So the diagonal is open, so therefore there is some neighborhood of this x times t in V times t whose image is in the diagonal. Now since t is finite, you can replace this V by the neighborhood of x, so that is some u times t. So now these two diagrams are precisely the same. Only difference is now we replace V with u and we get the required result. So there was not much to do. Basically we were given everything. So this alpha inverse h and beta gave you this map phi, and then you just had to do a little bit more topology, just these 4 lines, to make sure that we are talking about these discrete sets lying on open sets. So this was important, and then we can now continue forward to G1 to G6 and start checking the axioms. So the first axiom, we have to check 2 things. So the first is the terminal object. So the trivial cover, this is just the identity map. This is the terminal object of our category of covering spaces on X. And then we have to check the fiber product exists for any 2 objects. So the fiber product of any 2 objects over the third one exists. So what does that mean? So say we are given maps G and H. So you're given a map G and H, and all 3 of them are coverings of X. So that is all 3 of them have maps going to X. So then in that case we should have a fiber product which should look like this. So just the definition of the fiber product is this y and w, such that this y goes from here to here, becomes g of y, and this w goes from here to here, and then you apply h to it. They should be equal. So this diagram should make sense. So obviously you have map between covering spaces here, and these maps make sense from the lemma. So you take u small enough to get trivial covers, so as given in the lemma. So in this lemma we will able to construct this map phi going from u times t to u times e, and we had 2 covers y and z. So here you have 3 y, z and w. So now from this map, instead of this map, you have u times t1 to u times e. So this is your map phi 1, this is your map phi 2, obviously identity times phi 1, and this is identity times phi 2, because u just goes to u. So then, and all of them are sitting over u. So this u sits inside X. So you have taken u small enough neighborhood of some point X. So that is it. So now you take the fiber product of these 2 maps, which is just this, and this now forms a cover over u, and that is what we had to show. So everything will agree, just because this is a fiber product of this phi 1 and this phi 2. So this implies this. So G1 has been checked. The second and the third axiom are pretty straightforward to check. So for G2, initial object is just the empty cover, and say you are given a bunch of covers, say xi to x, you can all glue them together to get a disjoint union. So you construct a function f which is just disjoint union of this, and you restrict it to fi. So you can construct disjoint union, and you can also standard quotient space you can form. So given a finite covering like this, and say G is a group of automorphisms of y, you can just quotient this out considering orbits of y under G, and this quotient space becomes a finite cover of X. So just a standard quotienting out. G3 is again very standard. So you're given a morphism like this, h y to z, then you just split it. You write z as z1 disjoint union with z2. So here h1 is an epi and then this H2 is a mono. So this is a, you can think of it as a surjective map, and then you think of this as a injective map. So basically you split Z into two parts. One component comes completely from Y, which is Z1, and the other component is just which does not come from Y. For the fourth axiom we need to check is that this fundamental functor, it maps terminal objects to terminal objects and commutes with fiber products. So you're applying this fundamental functor to the terminal object, and you see by definition this fundamental functor is nothing but associating a fiber like this f inverse of x. So it just puts a f inverse, which is just the identity map. So you just get the singleton x corresponding to this x here, and the singleton is the terminal object in the category of sets. So the second is slightly more involved. We have to show that the functor commutes with fiber products. So this is our definition of the fiber product. So this is underlying space x, and then you have w, z, and y, and this is the fiber product here. This is standard projection maps. So now you apply this functor f of x to it. Again, applying this functor means that you are applying f inverse of x. So f is here. So here you will get f inverse of x. f1 is here. You apply this functor f of x to this diagram. So now we are sitting in the category of sets. So corresponding to this covering, you have the small x here. You have f1 inverse of x. Corresponding to this map, you have f2 inverse of x. And then you form fiber product like this. Over these two maps, you form the fiber product. So now this fiber product, in terms of applying the functor, because this inverse is what the functor is, this is fxy, precisely because this f1 inverse of x corresponding to this here, and then this f inverse of x corresponds to z. As you can see here, f inverse of x comes right here because f is here, and then fxw corresponds to f2 inverse of x because this comes right from here. So you have this map right here. So we are left to show that if you apply f of x to it, what you get is this, but this is equal to this. So what we are supposed to show is that this is equal to this map here, f1 inverse x, this pull back here, so that this will become this. So because this is equal to this, so we have to show this equality, which will show that this is commuting with the fiber product. So what we are going to show is this. So let us start by so this is what we will show from. We'll start from here and end up here, but let us start from the backward. So what does this mean? F of x, this y, z. So that basically, if you just look at here, that basically means you have some points here, y and w. This w gets mapped here, y gets mapped here, and they have to both agree here. So that is h of w is equal to g of y. So that is what is our standard definition. So this is what if you just apply this functor f of x would mean to it. So they have to agree here, but they are part of the covering space on x. So this x is also coming from this pair y comma w. So it has two journeys. One, it goes from here and then here. So that is, first you apply p1 and then f1, you should get x. So p1 and f1 apply to the pair, you get x, and the second journey is from here to here. So first you apply p2 and then f2, you should get x. So that is what you get. So rather than going through the pair, you could have taken this projection map, gone to w and then gone to x. So then it would just be f2 w of x. So rather than doing this projection map, you just have gone from y to x using this map f1. So that's what you do. But when you do this, what you get is this map, precisely because all these things carry over right here. Precisely because this w is coming here, this y is coming here after the application of this functor f of x, because this lies over this point here. So similarly here. And that's it. So by the definition of this fiber product, this remains, and these two have to equal x here. So you apply your corresponding maps, they should equal x here, which x basically comes from f inverse of x here. So that is pretty much it. So this is what it gives you. So this is just again an exercise in diagram chasing and understanding how fiber product works. So you just draw the squares and start chasing. These things become clear. So in fifth axiom we have to show three things. So the first thing we have to show is that f of x commutes with finite sums. So this is just a matter of writing it down. So again, you know, f inverse of x is precisely what is the definition of a fundamental functor. And so you're applying this to this map, taking all those. So this is what it means. Applying fundamental functor is these points f of a1 getting mapped to x in x1 and here, which basically is just disjoint union of different f inverses of x, which just gives you this. So it does commute with direct sum. This is just a matter of writing down what the inverse images would be in each of the sets here, which are lying over x. This joint union is lying over x. Second is commutes with quotient. So this is just group action. So again, f of x acting on this kind of a projection map is basically, again, you know, you have to think in terms of fiber over x. So you are just thinking of all those points y which are getting mapped to x, and these points y are getting acted upon by group G. And then basically this you recopy it here. So you now take all points of y, but the group action, instead of here, you take it out and modulo it. So once you have this, this is just again by the definition of fundamental functor, we are just looking at points y which are lying over x. So this you can just think of it as p inverse of x. So once you think of it as p inverse of x, what you get is this fundamental functor right here, f of x y over g, because this is just inverse of x. So it commutes with quotients. And the third thing is that it should send epi to epi, but that is kind of obvious because in both coverings and sets the maps are surjections, so it just sends surjections to surjections. And so in the last axiom G6, what we have is we have a fundamental functor. So say you have an object in covering space of x, and then we apply our fundamental functor to it, and then you land up in this space. So once you land up in this space, we are saying this is an iso, so we have to show this is also an iso. So as we have just seen in G5, there could be many objects which are disconnected, and therefore there could be many images here. So to get this, we have to talk about a connected object. So first we talk about a connected object of a category. So a sub-object x of some category C. So first we define what a sub-object is. So sub-object is just a monomorphism of y going into x. So this object x is called connected if it has precisely two distinct sub-objects, the null set, which is the initial object, as well as the object itself. So this definition, as you can see, is motivated by the definition of connected sets. So you can see definition of connected sets in topology, and this is just rephrasing it in terms of category theory. So now we assume x is connected, and we have a morphism h from y to z. So precisely this morphism h from y to z. So we are saying that this is iso should mean h is iso. So this fx of h, you can see fx is just this fundamental functor f inverse of x. So this is just the restriction of h to fibers over x, and h is bijective. So this h is bijective here if and only if this following map is bijective. This phi has to be bijective. So this obviously follows again from this diagram, precisely because this is a homeomorphism. So this is a bijection, this is a homeomorphism, this is a bijection, and this map phi we built from going alpha inverse h and beta. So bijection here will depend upon bijection here because these two are bijections anyway. So that's what. So h is bijective if and only if the map phi and the lemma is bijective. So consider two open sets, S1 where this is bijective and set S2 where this is not bijective. in X. So since X is connected, so these two sets should bisect bisect our set X, because there are only two possibilities: either this is bijective or it is not bijective. So something and not something. So these two sets should cover X. But X is connected, so one of the sets is empty. But to check the axiom, we have to assume that this is iso. So at least for some X, this has to hold. So this is bijective for at least one X. So if it is bijective, so this set cannot be empty. S1 cannot be empty. And since X is connected, it has to be the case that S1 is equal to X and the other set has to be empty, because the only monomorphisms are the null set and the set itself. And this is not the null set, so it has to be the complete set X. So therefore H is bijective, and because this will hold for every H, and therefore you have an isomorphism in the covering space of X. So all this material is obtainable or taken from this book called Galois Theory of Schemes by Lenstra. So this you can Google and you will get it. So I'm taking it from this book by Lenstra.